Types of relays and how they functions. Part 2. Relays are electrically operated switches that use an electromagnet to mechanically control a set of contacts. They are widely used in control systems, communication circuits, and other electronic applications. Here are some of the most common types of relays and their functions. A time delay relay is a type of relay that allows a circuit to operate with a delay before it opens or closes the contacts. This functionality is useful in applications where a time interval is needed before an action occurs or when an action needs to be held for a specific duration. Time delay relays are often used in industrial automation, HVAC systems, and various control applications. Structure and components. Coil. Similar to electromagnetic relays, the coil generates a magnetic field when energized. Timing circuit. This component controls the delay period. It can be implemented using mechanical timers, capacitors, resistors, or digital circuits in more advanced relays. Contacts. The switchable components, normally open or normally closed, that change state based on the timing circuit's operation. Adjustment mechanism. Many time delay relays have a knob or digital display to set the desired time delay. Working principle. Activation. When the control signal is applied to the coil, the relay is energized, but the contacts do not immediately change state due to the delay mechanism. Timing delay. The timing circuit begins counting down the preset delay period. The method of timing can vary depending on the relay design, mechanical, electronic, etc. Contact action. Once the preset delay time expires, the relay contacts will either open or close, depending on their configuration. Resetting. After the delay action occurs, the relay will remain in its new state until the input signal is removed or the relay is manually reset, depending on the design. Types of time delay relays. On-delay relay. The relay contacts close after the specified time delay when the control signal is applied. Off-delay relay. The relay contacts remain closed for a specified time delay after the control signal is removed. Interval delay relay. The contacts change state for a set duration after the relay is energized, then return to their original state. Programmable delay relay offers flexibility in setting different time delays and may allow for various timing functions through digital controls. Key characteristics. Timing range. The duration of the delay can often be adjusted from milliseconds to hours, depending on the relay design. Contact configuration can be configured as normally open, NO, or normally closed, NC, based on the application requirements. Power rating. The maximum voltage and current the relay contacts can handle. Advantages. Flexibility allows for timed operations and control circuits, enhancing automation and system efficiency. Energy efficiency can prevent unnecessary power usage by controlling devices based on time delays. Simple integration. Easily incorporated into existing systems without major modifications. Disadvantages. Mechanical components. If using mechanical timers, there may be wear and tear over time, leading to reduced reliability. Accuracy. Some older designs or mechanical types may have less precision in timing than electronic or digital alternatives. Applications. Motor starters. Used in motor control circuits to delay the start of a motor to prevent inrush currents. HVAC systems. Controls fan delays, allowing a fan to continue running after a heating or cooling cycle has ended. Lighting control. Ensures lights remain on for a certain period after a switch is turned on or off. Alarm systems. Provides a delay to allow users to disarm the system before triggering alarms. The time delay relay is a versatile device that enhances the functionality of various electrical systems by adding time control capabilities. Its ability to control the timing of actions in response to electrical signals makes it a valuable component in industrial, commercial, and residential applications. A latching relay, also known as a bistable relay or impulse relay, is a type of relay that maintains its last position, either open or closed, even after the control power is removed. Unlike conventional relays, which return to their default state when power is lost, a latching relay latches in place, requiring only a brief pulse to change states. This characteristic makes it ideal for applications where energy efficiency and maintaining state after a power loss are important. Structure and components. Coil. Most latching relays have two coils, referred to as set and reset coils. When one coil is energized, the relay changes to a particular state, either set or reset. Magnetic or mechanical latching mechanism. This mechanism keeps the relay contacts in their current position after the coil is de-energized. This may involve a magnetic field or a mechanical latch that holds the contacts in place. Contacts. The relay typically has normally open, NO, and normally closed, NC, contacts, which are held in position by the latching mechanism. Working principle. Set operation. When a pulse of current flows through the set coil, it generates a magnetic field, moving the contacts to the latched position. Latching. The latching mechanism holds the contacts in this position after the set coil is de-energized. Reset operation. A pulse to the reset coil generates a magnetic field in the opposite direction, which moves the contacts back to their original position. Power efficiency. Since the relay only needs a brief pulse to change states, it conserves power compared to conventional relays that require a continuous current to maintain position. Types of latching relays. Single coil latching relay. Uses a single coil and changes states by reversing the polarity of the input signal. Dual coil latching relay. Has separate set and reset coils, where each coil controls a specific state of the relay. Key characteristics. Memory function. Retains its last state even after the control power is removed, making it useful in applications where maintaining the relay state during power outages is important. Energy efficiency. Requires only a short pulse of power to change states, which minimizes power consumption. Durability. The latching mechanism reduces the need for constant power, resulting in less wear and tear on the relay components. Advantages. Power savings. Only consumes power during the switching operation, making it highly energy efficient. Maintains state after power loss. Retains its last state, which is valuable for safety-critical and memory-sensitive applications. No continuous coil current. Reduces heat generation and wear on components, increasing the relay's lifespan. Disadvantages. Complexity in control circuit. Dual coil latching relays require two separate control signals, which can complicate circuit design. Cost. Latching relays are often more expensive than traditional relays due to their additional components and specialized design. Applications. Lighting control systems. Used to control lights with a single push button that alternates the lights between on and off states with each press. Memory retention circuits. Ideal for circuits that need to maintain state during power outages, such as alarms or emergency systems. Automotive applications. Used in cars to keep circuits on or off without continuous power, like in central locking or power window controls. Industrial and building automation. Controls for HVAC systems, alarms, and motorized gates where maintaining the last state after power failure is essential. The latching relay is highly valued for its memory function and energy efficiency, especially in applications requiring low power usage and consistent state retention. Its unique ability to latch into a position makes it suitable for various automation, control, and safety applications. A polarized relay is a type of electromagnetic relay that responds to the polarity of the control signal. This relay has a permanent magnet in its structure, which makes it sensitive to the direction of the current flowing through the coil. Because of its reliance on polarity, a polarized relay is typically used in applications where the direction of current matters, such as in telecommunications, signaling, and specific control circuits. Structure and components. Permanent magnet. Provides a constant magnetic field, which helps the relay respond to the direction of the coil's current. Electromagnetic coil. When energized, this coil generates a magnetic field whose direction is determined by the polarity of the current. Armature. A movable component that interacts with both the permanent magnet and the magnetic field produced by the coil. Its movement depends on the direction of the current. Contacts. Normally open, NO, or normally closed, NC. Contacts that connect or disconnect based on the armature's movement and the current's polarity. Working principle. Current flow. When a DC current flows through the coil, it creates a magnetic field, whose polarity is determined by the current's direction. Interaction with permanent magnet. The relay's permanent magnet is set up so that it either attracts or repels the magnetic field created by the coil, depending on the polarity. Contact switching. If the magnetic field from the coil aligns with or opposes the field of the permanent magnet, it causes the armature to move and switch the contacts. Polarity sensitivity. The armature only moves if the current polarity matches the relay's specific requirements. making this relay ideal for polarity-sensitive applications. Key characteristics: polarity-sensitive operation. Responds only when the control current is in the correct polarity, providing selective switching. Quick response time. Polarized relays generally switch quickly due to the combined magnetic forces from the coil and permanent magnet. High sensitivity. Requires relatively low power to operate thanks to the aid of the permanent magnet. Advantages: precision control. Allows for precise control in circuits requiring polarity-sensitive operations, especially useful in complex signaling systems. Energy efficiency. The assistance from the permanent magnet reduces the energy needed to operate the relay. Quick operation. With the additional magnetic field, polarized relays typically have fast switching times compared to standard relays. Disadvantages: limited to DC applications. Due to its reliance on current polarity, polarized relays are typically restricted to DC circuits. Complex design. The addition of a permanent magnet and the sensitivity to polarity make these relays more complex than standard electromagnetic relays. Application-specific use. Since it operates based on polarity, its application is often limited to specialized fields. Applications: telecommunications. Commonly used in telecommunication systems for signal routing and transmission, where polarity control is essential. Control and signaling circuits. Used in control systems that require direction-sensitive responses, such as in railway signaling and navigation systems. Protective relays. Employed in protection circuits that depend on current direction for correct operation. Precision instruments. Used in instruments and measurement systems requiring low power and polarity-specific control. Types of polarized relays. Single coil polarized relay. Uses a single coil with a permanent magnet, switching based on the polarity of the current in the coil. Double coil polarized relay. Has two coils, and the relay's operation depends on the relative polarity of the current in each coil. The polarized relay is a specialized relay for applications that require precise control based on the direction of current. Its polarity-sensitive operation, coupled with fast response and energy efficiency, makes it ideal for telecommunications, signaling, and other direction-sensitive control applications. A differential relay is a protective relay designed to detect faults within a specified area of an electrical system, typically by comparing the difference between incoming and outgoing currents. This relay is used primarily in power systems to protect critical equipment, such as transformers, generators, and bus bars, from internal faults. If the current difference exceeds a certain threshold, indicating a fault within the protected zone, the relay will trip and disconnect the affected equipment to prevent damage. Structure and components. Current transformers, CTs are placed on both sides of the protected equipment, e.g., transformer primary and secondary sides, to measure the currents flowing into and out of the equipment. Comparing circuit. This circuit compares the current values from both CTs. It is often an internal part of the differential relay or protection system. Relay contacts. The contacts connect or disconnect the circuit based on the difference in current detected. Threshold setting. A preset limit that defines the allowable current difference. If the difference exceeds this threshold, it indicates a fault, and the relay will activate. Working principle. Normal operation. In normal conditions, the current entering and exiting the protected equipment is almost identical, or within a safe tolerance range. The differential relay measures this and remains inactive. Fault detection. If a fault occurs within the protected equipment, such as a short circuit or insulation breakdown, the currents at the two ends will no longer match. Differential current. The relay calculates the difference, or differential current, between the two measured currents. If this differential current exceeds the preset threshold, the relay activates. Trip signal. Once the relay detects a fault, it sends a trip signal to the circuit breaker to disconnect the faulty equipment from the power system, minimizing damage and maintaining system stability. Key characteristics. High sensitivity. Differential relays are highly sensitive to internal faults and can detect even minor differences in current. Zone protection. The relay is designed to protect a specific zone, such as a transformer, generator, or section of a bus bar. Fast operation. These relays have a quick response time, crucial for protecting high-value equipment from rapid internal fault escalation.